This is the first topic of shallow foundation. We start talking about the bearing capacity of shallow foundations. There are different types of design theories for calculating or for analyzing the bearing capacity of shallow foundation, and we will start with a very simple and widely accepted one proposed by Terzaghi. We have two objectives for this lecture. First, you will need to be able to explain Terzaghi's bearing capacity theory and know how to use it to calculate the bearing capacity of spread footing. Second, on top of that, you need to be able to apply Terzaghi's bearing capacity theory to design spread footings under different groundwater conditions. That is, when we have water table at different depths. So before we start introducing Terzaghi's bearing capacity theory, let's first offer some basics about shallow foundation and design. And if we zoom out and take a look at the whole foundation engineering foundation design course, we will see that we have three major components. First, we talk about shallow foundation. Then we move to steep foundation. And finally, we will cover earth retaining structures. So for shallow foundation, so what are shallow foundations? From their names, we can see that they're kind of shallow. And I will offer a criterion to tell what a shallow is shallow for shallow foundation. And shallow foundation can be divided into two categories. One category is spread footings. So spread footing can be viewed as an enlargement at the bottom of a bearing wall or a column. The reason that we want to cast and install this enlargement at the bottom of a wall or multiple walls or a column or multiple columns is that if we put the walls or the columns on the soil directly, it's very easy to break the soil because we know that the soil is pretty soft. So if we put an enlargement to enlarge the contact area between the wall or the column and the soil, we will reduce the pressure. In that way, we can sustain a higher load from the wall. In early days, usually the enlargement was masonry. We can use materials like dimension stone, like a rubble stone. But in modern construction industry, now we typically use concrete. And we can have different shapes of enlargement, such as square and rectangular. Circular, and we can also have something called continuous, for which I will explain more. And of course, we can combine these different basic shapes to make something that's more complicated. Sometimes we need to sustain very high loading within a very confined space. And if we still try to design one or multiple spare footings to sustain such type of load, we will find that we need to have a lot of spare footings and they overlap each other. So some people then think, why not just combine these spare footing and connect them? In that way, we will get the mat foundation. So they're connected. Usually, they are wide, but they're thinner than spread footing. The design philosophy, geotech part of the design for spare footing and mat, they're very similar. But the structural part, we will have some extra structure analysis for the mat foundation to make sure that the mat foundation will not break because they're wide and not as bulky as the spread footing. So in this course, we possibly won't have time to cover the mat foundation. But as mentioned, the geotech part of the design, they're similar. If you know how to do design spare footing, then you should know how to conduct analysis for the mat foundation. So let's take a look at spread footing, what it looks like. I'll first draw a 3D view. Let's assume that we have a column and we have load coming from the superstructure. As mentioned, if we put the column on the soil directly, it's very hard for the soil to sustain the load directly. So in order to enable the soil to sustain such a high load, we want to enlarge the contact area by building a spread footing under this column. As a result, we will have something like this. And usually the spread footing is buried in the soil. So that means the bottom of the spread footing is below the ground surface. And it can have different shapes, as we just mentioned. So assume that we have a rectangular spread footing. We're going to have 2 dimensions along 2 different horizontal directions. And if they are the same, then it's a square. If they're not, it's rectangular. Let's call one B and one L. Usually we assume that L is length and B is the width. And for design, one common rule is that we want to analyze the most dangerous case. That's the worst case. And if the foundation, the structure can survive in the worst case, then it should also be able to survive in other cases. And for the consideration of the bearing capacity of the shallow foundation, if we analyze the bearing capacity along 2 directions, and we will always find that the direction with the shorter dimension will be a worst case. So in that case, B, this cross section represents a more dangerous case. So to better show this, we usually draw the cross section of this 3D spread footing in a 2D way. So we have the column and the spread footing, and the ground surface is here. As mentioned, because this direction is more dangerous, so this should be B rather than L. But if you don't believe this rule, you can do the analysis yourself to analyze B and L. You will find that B on this direction, we will have a lower bearing capacity. The distance from the ground surface to the bottom of the footing is D. This is called the depth of embedment. There are a few other things. One thing we want to analyze is the pressure between the bottom of the spread footing and the soil right below it. And if we assume that the total load from the column, from the superstructure is F, then this one we can call it P. So P is called the bearing pressure. It's actually the resisting pressure provided by the soil to sustain the superstructure, the column. So if you do the static analysis, you'll find that P equals F, the total force, divided by A. A is the contact area, so it's the area of the bottom of the spread footing. And for designing this spread footing, usually what we need to determine is things such as D and B. So how wide the spread footing should be and what is the depth of embedment. We adjust these two parameters, we will change the bearing capacity of this system. So after introducing these basics of shallow foundation, let's also talk a little bit about design. We need to know some basic rules and terms for design. So the first thing that we want to know, that is the design method. In foundation engineering, usually we use the allowable stress design, ASD. So this one is kind of the simplest design method. We can use one simple criteria to tell how to use ASD. That is, we have something called a load or demand. Should be smaller than the ratio between capacity and the design safety factor. So capacity, that's the resisting load, resistance. That's the force that can help stabilize the structure. And the load, that is the load will fail the structure. So these two types of forces compete with each other. And safety factor is the ratio between them. If we write this using the symbols in foundation design, we will have P, small letter p. So that is the load need to be smaller than Q sub U. This is the symbol that we use for capacity divided by safety factor, design safety factor. So SF design. Sometimes we also use FS for the safety factor. It's the same thing. So this Q sub U is the bearing capacity. And a P. Here you can see that we have this bearing pressure. It's the same thing here. But in later lectures, we usually don't use this equation directly. Instead, we do it in this way. We first reformulate this equation a little bit. So we said that QU over P. This is actually also safety factor, but it's the actual safety factor. So this ratio need to be greater then. So you can obtain actually by move SF here and then move P here. So we get QU divided by P should be greater than SF design. This is the criteria that we will use to tell whether the design is adequate or not. This is for ASD. And if you have ever taken some other courses for design before, such as that for concrete and steel, you may have seen some other design methods which look much more complicated and fancier than the ASD. And one thing that you possibly have seen before is something called a load and resistance factor design. LRFD. So for different design methods, we just come up with different ways to account for the uncertainty, the risk. And for ASD, we just use one safety factor. We try to use a safety factor that is higher than 1. So you can see that if safety factor is 1, that means QU, that's the force that it will stabilize the structure, equal P, that's the force that will fail the structure. So they were exactly the same. So that means the structure would have a very critical state. If the P increases a little bit, the structure will fail in theory. But in reality, we have a lot of uncertainty in materials, in contact, in construction. So if we make these two equal in the design, what's going to happen is that it's very easy for the structure to fail. So in that case, we want to raise design safety factor so that, even we have some bad things, uncertainty, the structure can still survive. In ASD, we only have one factor to consider all the uncertainty. In the LRFB, you can see that we have different factors. So instead of use one safety factor, we have different factors, for example, for different types of loads, for dead load, for the live load. This LRFD has been used for concrete. It has been used a lot. And for steel, and it has been used, but not as often as that in concrete. In timber, it's even less often. There's another type of design approach which is even more advanced from the perspective of risk control. That is something called reliability-based design. So for this one, instead of using different factors, they use probabilities directly. So that's even more advanced and fancier, but of course more complicated. In foundation design, people found that ASD is good enough because, and also of course we have some other reasons. One reason is that the uncertainty is too high. It's really difficult to allow for different types of risks. So instead of use very fancy stuff, we prefer the simple one that can save a lot of effort in design and which is also proven to be adequate in the practice. And one more thing for design is, in addition to the designing method, is we have different considerations. So the primary consideration in foundation design is usually associated with strength or stability. And I want you guys to think about one question. So what is the difference between strength and stability? The difference actually is that strength is something associated with materials, but stability is a value associated with not a materials anymore, but a object made of some type of material. That means the dimensions and the position of the object matters. in addition to the material properties. So you can see that now. That's why we call bearing capacity. We don't talk about strength anymore. But the bearing capacity actually comes from strength, location, and other things of the foundation. So that's the primary concern. And also we have some other secondary concerns. That's for serviceability. The strength, the stability concern is primary because that is related to our lives. If a structure fails, we will lose our lives. So that's the primary. And for secondary, serviceability, for this type of design concerns, if we have some issues associated with serviceability, for example, you got some water in your basement, and you will find that possibly you can still live in your house. However, that's not the intended use of the basement. Even you can swim in. That's not what you designed the basement for. So that will hurt the serviceability of the basement. So it will not threat your life, but it will hurt the intended use of your structure. And for this one, we have a lot of things such as just mentioned, such as water concerns, and one serviceability consideration that will be made in this course is associated with settlement. That's a deformation. For example, if you find that you cannot open your door, the building may still be okay, but the service, will be interrupted. So you can see that the design considerations in foundation engineering, they're actually related to what we learned in soil mechanics. In soil mechanics, we said that we have three basic issues. We have water, drainage, seepage issue. We have deformation, settlement issue. So they are secondary. And we also have strength. So that's for stability. That's primary consideration in foundation design. So you can see the connections between soil mechanics and foundation engineering. Next, let's continue and move to the design theory. As mentioned, we have different design bearing capacity theories, and Terzaghi was one of the earliest one. In the following lecture, we will be talking about another theory. It's called general bearing capacity theory. So that one is more comprehensive and can overcome some issues that cannot be addressed using the Terzaghi's bearing capacity theory. So this theory is associated with one equation for calculating the bearing capacity. This actually can be derived. But at the very beginning, it was derived for the continuous footing. Not square, not a rectangular. The reason is that the continuous footing can be simplified from a 3D case into 2D. And if you ask what is a continuous footing, or what do you mean by continuous, you can think about a dam or a levee. So what is the common traits of a dam and a levee? And possibly what will pop up in your mind is that they're kind of very long, right? So in summary, they have three dimensions, but one dimension is much greater than the other two. And also, along that long dimension, we have different cross sections, and these different cross sections will be identical, just like a dam. And because of that, if we assume that we have the same loading along that long dimension, let's call it X, we can expect that along different cross sections, we will have exactly the same process or loading conditions, both inside and below the foundation. As a result, analyze the 3D structure, we just need to select one cross section and just analyze that cross section. So we can simplify the 3D condition into 2D. And for this 2D condition, we can derive a analytical solution for the bearing capacity. So here I will not do that. Instead, I want to ask you guys one question. So we know that we need to calculate the bearing capacity Q sub U. I want you guys to think about. So if I want to place a spread footing in soil, let's say it's not a real spread footing, just put an object into a sand layer, and I want to put a load on that object. I want to push it into the soil. So if I want to improve the bearing capacity, that I want to increase the load that object can sustain, what can I do to the soil or other things so that load the object can sustain can be raised? Think about it. What can we do? One of the first things coming to my mind is that I can, for example, use the sand. I can put some glue in the sand, right? So in that way, can the load be raised? And you will say possibly yes, because it seems that the soil becomes more rigid. If we add some glue to it, the bonding between the particles was increased. So if we're talking about the soil, you talk about the more Coulomb criteria by adding some glue to it. Which parameter, C, phi, do we change? It's a C, right? C is the cohesion, so that's kind of the bounding. So the first component of the Q sub U is the cohesion. That is, if we add a glue to the soil, we'll change this part. People found that Q sub U is proportional to the C prime. Here, prime again is for effective. And this proportionality is a constant called N sub C. If there are any other ways that we can use to improve the bearing capacity of the object? So what if I place some sandbags on the sand surface? Will that help stabilize the object or enhance the bearing capacity? Intuitively, it seems that's possible, right? Actually, that's also the truth. So the second part is associated with Q. So Q is the surcharge. Just like if we put sandbags on the ground, that will increase the confining pressure on the vertical direction. That will also help stabilize the structure. And the Q sub U is proportional to Q, and the proportionality is N sub Q. The last one. Can you think of any other things? What about replacing the sand with, for example, steel sand, which have higher density? Can that help stabilize the object? Seems that it could be a good idea, right? So if we do that, what we change is the unit weight of the soil. So it's gamma. So it's gamma and gamma. That's also the proportionality. But traditionally, we add a 0.5 in front of this term because the footing is symmetric. And also, the width of the spread footing matters. And if you consider the bearing capacity of the other direction, that's the L direction, here you need to replace B and L. But you can see that B is smaller than L. So if we consider the B direction, it seems that Q sub U will be smaller. So that's why the B direction is more dangerous. And in this example, NC and NQ and N gamma seems to be the key things, because we know C prime, we know Q, we know gamma. They are the material properties. If we don't know them directly, we can get them from the indices that we obtain in the subsurface exploration testing, which was introduced in the previous lecture. NC, NQ, and N gamma are bearing capacity factors for cohesion surcharge and a unit weight. Of the soil, respectively. These things can be obtained using, for example, table 4.1. And for coding purpose, it's more convenient to use equations. And in that case, we can use equations 4.13 and 4.15. And we will practice how to get these n numbers directly using the equations in the following lab. And to better understand the three contributors of the bearing capacity and their correlation with what's happening in the field, so I want to draw the following schematic. And I will offer a little bit theory relevant to the deduction of the bearing capacity equation. So ground surface is here. And here, this is B. That's the width. A critical surface that you guys need to keep in mind, that is the bottom of spread footing. If a failure would happen, usually it looks like something like this. So a shear surface could be like this. And this is symmetric. This is what a slip surface looks like. So in this case, for example, if the slip surface is this one, then the footing will overturn. So the surface will become something like this. And for the soil, it will bulge up like this. This is obtained by soil plasticity theory. So usually we have different names for these regions. This one is called a triangle zone. Triangular zone. And this two, they are the radial shear zone. And these two, they are the passive zone. Because the slip surface starts from here, these 2 points, and they propagate like this. And this soil body here have to move because they receive load from this radial shear zone. So that's why we call it passive. And the Q here that we mentioned actually is the vertical stress here. So this is the surcharge. So it's not the pressure on the top, it's the pressure here. So Q actually is the sigma Z0 prime. Again, is the effective vertical stress at this depth. So to calculate this Q or sigma Z0 prime, we need to see what soil layer or layers is above this line. So if there's only one layer and it has a unit weight of gamma, then just gamma H here, just this D. But if there are multiple layers, we need to do it layer by layer using the theory that we learned for the stresses in the ground. And on the right, we have the same thing. So this is also Q equals sigma Z0 prime because the whole thing is symmetric. And this is the angle alpha. So in Terzaghi's theory, we assume that equals to the effective internal friction angle. And this line is actually a logarithmic spiral line. You just need to know this. You don't need to understand why we have this type of shape. The whole thing is about a continuous footing. And what if we have some other types of footing? For example, square. So square is more complicated than the continuous footing because it cannot be simplified into 2D case directly. But people found that for the bearing capacity, we still have contributions from 3 parts: cohesion, surcharge, and unit weight. It's very similar, but the ratios of the 3 contributions will be different. So we still have C prime and C Q. You can see that leaves some space here. Q times NQ plus gamma B and gamma. Now the ratio is a little bit different, so we change the constants. Here is 1.3, and NQ here, this is 1, does not change, but here this becomes 0.4 instead of 0.5. For circular, it's also 1.3 times C prime times NC. And the Q term is the same. Q times NQ plus, now the last term, we change 0.4 to 0.3 times gamma. So that's not B, gamma B and gamma. And the last thing that we need to discuss, in all the above theories, we just use one gamma and use one Q. And we will see that when we have water table at different locations, these equations will be slightly changed for the calculation of Q sub U. So let's discuss groundwater conditions. And 2 things will be impacted by the position of the groundwater table. So Q and gamma could be affected by the depth of water table. We can see that we have 3 different conditions. So ground surface is kind of a critical depth. The second critical depth is the bottom of the footing. And the third depth is the bottom of this radial shear zone. The simplest case is that when there's no groundwater. Also, if there's no groundwater, we can also think that the groundwater is very deep. It's very far from the foundation. So how far is far enough so that we will overlook the groundwater table? That actually is when the water table is below this depth. After many observations, some people found that from the bottom of the foundation to this depth beyond which the groundwater will have no effect, people believe that it's very close to B. And the distance from here, ground surface, to the bottom of the foundation, this is actually the depth of embedment. If the depth of water table, let's call it dW. So this is the depth of water table. If this one is below D plus B, that means it's somewhere below this boundary of influence. Then in that case, the water table will neither affect Q, because the Q is affected by the unit weight above it. So if it's here, then it will not affect Q. And the gamma here is the average gamma in this zone. So between D and D plus B. So this is the gamma. So if water is below this, that will not affect the gamma here. So the first condition, no effect if dW is greater than D plus B. Second condition, so what will happen if dW is between D and D plus B? Will it affect the Q, the effective stress here? No, right? So the second condition, if dW is greater than D but is smaller than D plus B, in that case, first Q is not affected. But gamma will be affected. For example, if dW, in this case, this is case 1. If case 2 is here, then we have part of this zone below water table and a part above it. And for the part below it, for the case 2, we need to use the gamma prime. That's the buoyant unit weight. And above it is the natural unit weight. So we need to add them up and get the average. And this is actually the weighted average. And the weight is the depth of this submerged zone and zone above the water table. So for this gamma, we use gamma bar. So that means an average. This is an average. Here I'll give out the equation directly. So if you are interested, you can derive it yourself. It's gamma prime plus dW minus D over B, then times the difference between gamma and the gamma prime. And the gamma prime here, this is the submerged unit weight. So it's the difference between the saturated unit weight and the unit weight of water. So this one is the buoyant unit weight. So that is the second condition. The third condition, that's when the water table is here. So it is above the bottom of the footing. So in that case, you can see that first, of course, the Q here will be affected because now even there's only one natural layer. Now the natural layer is divided by the water table into two sub-layers. One layer has the natural unit weight, and the other one below it, we should use the buoyant unit weight for calculating the effective stress. So third condition, when dW is smaller than D, so first Q is affected. And if you need an equation, so I can do it here, Q equals gamma times dW. So you can see that gamma is the natural unit weight. dW here in this case is from here to here. Then this is dW. This is the first sublayer plus the buoyant unit weight, gamma saturated minus gamma W times the thickness of the second sublayer is D minus dW. So that's calculate Q. And for gamma, because all this zone now is submerged, so the average unit weight here is the buoyant unit weight. So we don't need to use this equation anymore. So this is how we need to do the bearing capacity analysis when we have different groundwater conditions. We just need to tell which case we have. And then we need to see whether this case, the groundwater will affect the Q and the gamma or not.
I think I'm falling for you.